We have the candidate now has 20 minutes to present her results. And then we have up to, including these 20 minutes, 90 minutes of discussions. And then afterwards, the committee will be in private. And if the technician says we can start, then I would say, let's start. And we're looking forward to your presentation.
Thank you, Professor Armin. Okay. Hi, everyone. So my thesis is about distributed approximation algorithms for graph problems. I would like to thank Fabian, my supervisor, as well as the rest of the jury members, Professor Al-Kida, who I cannot see on the screen, however I know is there, Professor Christian, and Professor Armin for being here today.
Sorry to interrupt you already.
Yes.
The thing is that I don't see the slides. I mean, I see Salva presenting and I see the screen in the room, but yeah. Perfect, thank you.
Can you hear me, Al-Kida?
Yes, I can hear you, yes.
Okay.
And I can see the slides now. Thank you very much.
Okay, so let's continue. All right. So in this thesis, we study two classical graph problems on node-weighted graphs. In the minimum weight vertex cover, the goal is to find a subset of nodes that cover all the edges while minimizing their total weight, like the orange nodes in the example. In the maximum weight independent set, the goal is again to find a subset of nodes, but now they should be non-adjacent while maximizing their total weight, like the blue nodes in the other example. Okay. I hope we're here. Okay. So these two problems are known to be... Okay, now I cannot move the slide. Okay, good. So it's known that these two problems are very closely related. The complement of a vertex cover is an independent set and vice versa. So if we look at their optimal solutions, they are equivalent. However, this equivalence does not preserve approximation. In fact, in the centralized setting, not only are both of these problems hard to solve optimally, but also for vertex cover, it is hard to approximate below factor 2 in general graphs. For independent set, it's much harder, not even a constant approximation in general. So centrally, things are hard. What happens in the distributed setting? We work with standard distributed models where the system is modeled as a graph. Every node is a processor, and initially nodes have only local information like their unique lock and bit IDs and any other general assumption needed. And the algorithm where we have communication proceeds in synchronous rounds, where in each round, every node can do arbitrary local computation, exchange messages with its neighbors. In the local model, the message sizes are arbitrary. In the congest, it's restricted to log n bits. And note, most of our problems, or all of our problems, work in the congest, so the more restrictive congest model. At the end of the algorithm, so after a specific number of rounds, I want every node to output its part of the solution. So whether it's in the independent set or in the vertex cover or not, okay? Now, these two problems are inherently global. So even in this distributed setting, they remain hard, even on simple graphs. To see this, let's consider an even length path, unweighted, so every node has weight 1, you can see it like that. And one can observe that in such graphs, there exists one unique optimal vertex cover solution, which is disregard the endpoints, take every other node like the orange nodes, that would be it. So intuitively, for a node to know whether it belongs to this unique solution or not, it has to check whether it's at an even or odd distance from some endpoint. And for that to happen, this would require the information to traverse the full path, which would require diameter rounds, and diameter can be as big as n, and in the local model, everything can be naively solved in that many rounds. So for vertex cover, exactness is hard, as well as for independent sets. A natural question would be, how well can we approximate these problems? And this is the question we address for both problems on general graphs and more special graph families where one can exploit their properties for better guarantees. So we will do so in parts 1 and 3 of the talk. And as we go from vertex cover to independent set, we develop a general de-randomization framework for many graph problems, not just these two, where essentially you have a simple randomized algorithm, you can efficiently transform it into a deterministic one while approximately preserving its performance. So we'll see more on this in part 2. And I will end by concluding statements. So let's start. Oh, yeah, before I continue, I will only be presenting the main contributions in this talk today. So we start with vertex cover. And we look at the unweighted version of the problem. So remember in the centralized, we said getting better than 2, it's hard. So the question, can we beat this barrier in this distributed setting? So in other words, can we get a 2 minus epsilon approximation for all epsilon? So you can see this as a near optimal solution. Other way to see it, 1 plus epsilon for all epsilon. That's easier, so I'll stick with that. And the answer is yes. So let's first talk about the state of the art. In the local model for general graphs, Ghaffari et al. Found a polylogarithmic time algorithm for solving the problem. So polylogarithmic here is considered efficient. Goose and Swamila, on the other hand, show that no sublogarithmic time algorithm can solve the problem, even on bipartite graphs. In congest, things are harder, what's known as optimal squared. So optimal can be as big as n. So slow, because in congest also it's known that anything can be solved in n squared. This was the state of the art of the problem before our work. So now let me highlight our contribution. We get a tighter bound on the problem for bipartite graphs, log n over epsilon, which naturally extends to general graphs. On the positive side, we get polylogarithmic time algorithms for the problem for bipartite graphs in randomized and deterministic. Notice for randomized, it's log n over epsilon cubed. So for a fixed epsilon, this would match the lower bound because the lower bound also works for randomized. Now, before I continue highlighting our contributions, let me give you the high-level idea of the general framework that we use for our randomized and deterministic results. Okay, the goal is to find the 1 plus epsilon approximate vertex cover for bipartite graphs. I will name the solution C, initially empty. The first step is to compute a special clustering with some properties. The key properties are, we have low diameter clusters. They are well separated, so this is not a partition of the graph. You will have some nodes unclustered. And most importantly, I want the subgraph induced by these unclustered nodes, so the outside world, to admit a vertex cover that is very small with respect to the optimal solution. This way, I can start handling the outside world first by computing a constant factor vertex cover there, so at most epsilon over 2 of the optimal, and add it to C. So now you can see every node whose both endpoints are not clustered now will get covered. However, there can be some edges where one of the endpoints is clustered, the other is not, that is left uncovered. So to handle these, every cluster can check if it is incident to such an edge, and then it will extend itself by 1 hop to contain it. And because we have well-separated clusters, no 2 extensions will interfere with one another. Okay, and then locally, in parallel, every cluster can compute a good approximate vertex cover. So for example, 1 plus epsilon over 2 of the optimal, and add it to C. Now, combined with the outside solution, C will become a 1 plus epsilon approximate vertex cover. You can check this easily. Now, how fast can we do this? Well, all of these steps can be done in polylogarithmic time, randomized and deterministic. In particular, step 3, so we can do this all polylogarithmic time. In particular, step 3, so here we're trying to solve the problem on the clusters, right? A 1 plus epsilon approximation. But one of our contributions is also that if you know you have a bipartite graph, you can solve this in time linear in diameter. And because we have bipartite graphs and the clusters have low diameter, this is efficient. We continue with our contributions. So now we move to the weighted minimum vertex cover problem. And This general framework we saw, and all of our results for the unweighted also extend here. So we get the same runtime for all of these. So this is the same table we saw for unweighted, also applies for weighted with, of course, extra technical work. Now, if we move to the more general case, and specifically for graphs that are closed, undertaken, induced subgraphs, this includes graphs like planar graphs and other important graph families, we know we have the following result. So if we can compute an independent set of heavy weights, so of weight at least, say, lambda of the total weight of the graph, then we can get a 2 minus 2 lambda plus epsilon approximation. So for non-negligible lambda, this would be something better than 2, all right? And we can do this in polylogarithmic time plus the time to get an independent set. So what have we seen? We have seen near optimal solutions for the bipartite case and partial progress for the general case, where we can reduce this problem to computing heavyweight independent sets. So to deal with this independent set problem and many others, we have this general de-randomization framework, which I will discuss next. All right. So what is it about? It's based on a technique called local rounding, where the high-level idea is to start by defining a solution fractionally, and then round it until you get an integral solution, gradually round it. But we do so while essentially preserving the fractional quality of the solution. This will make sense as we go. But before, let me give you a recap of the background on what we know about local rounding in the distributed setting. Okay, so Hankovic et al. Find the first polylogarithmic time algorithm for maximal matching. This is a matching that cannot be extended using local rounding. Fisher then improved on this runtime using, again, local rounding. After that, Fisher and Ghafari found the first polylogarithmic time algorithm for 2 delta minus 1 edge coloring. So this is a coloring on the edges such that no two incident edges have the same colors. Using, again, local rounding. Harris improved on this runtime using local rounding. And then Ghafari and Kuhn found the polylogarithmic time algorithm matching all the other time complexity of vertex coloring. So this is the coloring on vertices using, again, local rounding. Now, the problem was all of these local rounding approaches were problem-specific, tailored mostly to matching or coloring, and did not extend to other problems, like maximal independent set, an independent set that cannot be extended, where together all three make up 4 central problems in the distributed computing field. So this lack of a unified approach motivates our work, and we give a generalized local rounding approach that, generalizes all of the others, previous ones, significantly. And note, before I keep going, all of these results work in the local model. So even for MIS, the best known was log to the power 5n, and with our unified rounding, this is improved to log squared delta log n, matching all of the other 3, where we can also apply our local rounding to and get the same runtime. For congest, we can also apply our unified rounding to matching and independent set, mistake, and not a mistake, but we can also apply it to other problems, like minimum set cover, where we can get an approximation ratio same as what a sequential greedy algorithm would give you, close to what it would give you, in polylogarithmic time and SNT. SNT are local parameters in the set cover instance. So this result improves on previous results because before it was polylogarithmic in only n with substantially higher powers. And there are other applications where one can use our local rounding too. I will not get into it, but namely maximum weight independence set. This I will get into it at the end. For now, let me illustrate this method on the basis of an example. And the goal is, you have a graph, you want to compute an independent set of size big omega n over delta. Delta is the maximum degree. So there's a simple randomized algorithm that solves this. Every node marks itself independently with probability 1 over delta. And then every edge checks whether both of its endpoints are marked. It will remove the lower ID node or unmark the lower ID node. So now the set of marked nodes you can hopefully see is an independent set. And with size, well, in expectation, it's going to be the expected size of the marked nodes. Some calculations tells you it's n over delta, simple calculation, minus the expected size of the unmarked nodes, which we can upper bound by the sum of all of the edges whose both endpoints are marked. So with simple calculations, you can see it's n over 2 delta And thus, you achieve an independent set of size n over 2 delta, achieving our goal. However, an expectation, right? We want to do this deterministically. We want to achieve our goal deterministically. And we'll do so by de-randomizing this algorithm via local rounding. Okay, so we said we want a fractional solution. Let me define the fractional version of the problem so that fractional solution makes sense in here. And the idea is we want to assign for every node a fractional value between 0 and 1. And I want to interpret it as the probability of the node being marked when I plug it in my randomized algorithm. So now I would get an independent set with expected size, the same analysis as we did before, but now I can rewrite it as this expression using these fractional values. So this expression, I will call it fractional quality. And now what's the goal? The goal is to assign fractional values for every node. And this would be my fractional solution. That's what I consider, such that this fractional quality attains the goal. So it's in big omega n over delta. All right. Now we gradually round these values. So we will proceed in rounding phases, where initially every node has a fraction value 1 over delta. What it will do locally is round itself either up, so 2 over delta, or down 0. And then we'll do this along the phases. So we would need log delta phases to get an integral values. 1 is I'm marked, 0 I'm unmarked, and this is done deterministically now. So, but we don't want to do this arbitrary. We want to do each rounding phases such that this fractional quality I described does not drop too much. So if we can attain this goal for every rounding phase, we get at the end an independent set, deterministically, whose size is this fractional quality at the end, which is approximately going to be equal to the fractional quality initially, which we already know is in big omega n over delta. Okay, so I will not explain how we attain this goal, but we can do this efficiently in log delta rounds. So you would need log squared delta with the number of rounding phases to achieve our goal. Okay, let me just now do a recap on this local rounding even more generally. This was an example. So we work with graph problems where each node has to choose a label from a set of labels subject to a global constraint. So in our previous problem, every node is either in and out. We had 2 labels, or marked or unmarked. And then we define a fractional solution where the idea is to assign for every label, so for every node should assign to each of its label a fractional value between 0 and 1 such that the sum is 1. So you can see it as a probability distribution for some randomized process. And then based on that, we define this fractional quality. Intuitively, it's the expected value of this randomized solution. But I want you to see it like this. This was our example from before. So a linear combination of pairwise interactions, pairwise local contributions. The local contributions are my fractional values of the endpoints of the edges in the sum, okay? Or just the node if you're summing over the nodes, which you can do. More generally, I want you to see it as a positive part minus a negative part, capturing benefits and conflicts, for example. Now, what we do next is we round these fractional values, and we want to do this strategically such that this fractional quality, this phi, is approximately preserved. And that's something I didn't say. In order to be able to do so in each rounding phase, we want to satisfy a key condition, which says that the positive part and the negative part should be sufficiently separated. Now, to see why is this needed, the idea is that in each rounding phase, you will have some negative loss from the old phi. So if you know that the positive and the negative part is sufficiently apart, then you can show that this negative loss is very small with respect to the old phi. So now the loss per one rounding step is not going to be too much. And if you do this, if we can attain this throughout all of the rounding phases, we get an integral solution at the end where the phi where we preserve the initial phi up to some loss. Okay, enough with local rounding now. Let me move on to independent sets. So recall, we used local rounding to show this goal, right? We wanted an independent set of size, this n over delta. So delta. Why is it important? Well, it is known that an MIS, so an independent set that cannot be extended, gives a delta approximation to the maximum independent set problem, so the unweighted version of the problem. So computing an MIS will compute a delta approximation. The question is, can we compute a delta approximation faster than MIS, so without passing through MIS? And this is the question that was addressed by Kawarabaishu et al., where they show the problem even on the weighted version of the problem, so they can get an independent set whose weight is almost a delta fraction of the total weight of the nodes, so not just the optimum. And they do it in polylog-log and randomized faster than computing an MIS for a specific range of delta due to a known lower bound by Kuhn et al. Now, they asked, can we do this deterministically? And we answered affirmatively. We can achieve an independent set of the same guarantee in the box above, deterministically, in log-squared delta rounds, faster than computing an MIS for a specific range of delta due to a known lower bound by value et al. So there are other approximation guarantees for the problem that we solve. I will not list all of them. However, I will list some. So in the unweighted case, it is known that there exists an independent set whose size is at least this this bound here, which is called the Caraway bound. And one can show a generalized, weighted generalization of it, so such an independent set of such weight also exists. And if you want to see it, so if you know Luby's algorithm, run one round of MIS, and you attain such an independent set in expectation. What we do is we attain such an independent set almost, so 1 minus epsilon, deterministically in roughly log cube delta rounds. Now, there are other weighted generalizations to this Caraway bound, so I will not go through them, but one can achieve, for example, this one via greedy approaches, sequential greedy approaches, and we give the first deterministic algorithm that achieves this almost efficiently. And so, yeah, we have more results as a function of arboricity. So if we look at bounded degree arboricity graphs, these are a special class of sparse graphs. We can improve on some of the state of the art of the problem. So the runtime approximation ratio trade-off, we can improve on that. For some cases, I will not mention all of them. I will choose to talk about trees. Yes, I'm done. This is the end. So this is the simplest, sparsest graph. Yeah, simplest, sparsest graph. Before they achieve a 2 approximation rooted trees, log star tight, we achieve near optimal solution. In general, unrooted trees, log star n over epsilon tight, we also prove the lower bound. So we'll stop here. And to conclude, well, just this minute, to conclude, so there are still other directions for further improvements in distributed graph algorithms. For independent sets, you can still think of improving this runtime approximation radio trade-off of the state-of-the-art for general graphs and other special graph families. This is still interesting. More generally, our framework is versatile. So an interesting question. Where else can it be used? And for vertex cover, the major question is getting this less than a 2 approximation for general graphs deterministically in the congest model. Can we do this efficiently? And finally, recall that vertex cover independent sets are related. So a natural question, how far can this relationship be exploited to gain better guarantees for both problems? With that, I now conclude. Thank you.
So thank you.
Yes.
So usually I would do this with the external reviewer first, because last time I was sitting here, Wolfgang Boert was going first. So I would ask the external viewer to ask a first round of questions, and then Fabian Kuhn, the supervisor, next. Then I don't know the English term of your role, but like Christian Schindelhauer, and the shotgun, and I'll will go last, and then we'll try to do another round, and maybe if time permits at the end, also ask the.
Okay.
So Ms. Bayou,